Hello everyone, welcome to Mindspan Education. So far we have reviewed a few concepts from linear algebra and calculus, and we have only looked at those things which we may need further in this machine learning course. I am going to do the same with probability. I will not go through each and every concept that we have already dealt in our probability and statistics course. I will only cover those concepts which I think will be required further in this machine learning course. And if you want to have a greater details or good understanding of probability and statistics, I would recommend you to go and watch my playlist on YouTube, and it is completely free of cost and it covers everything from basic to advanced. And if you want to do many practice problem, then I would recommend you to go and enroll into this probability and statistics course, where you will get, I think, more than 250 chapter wise practice problems. Right now, let me repeat one more time that I will not cover every topic of probability here. I will be only focus on a few concepts that we haven't deal in our probability and statistics course, but it is required here in this machine learning course, right? So anyhow, in order to proceed further, you must already have a solid understanding of probability and statistics. Otherwise you will face a lot of difficulties in understanding this machine learning, and you will not be able to build up the intuition of this subject, right? So it is strongly recommended that you need to go through the course of the linear algebra, probability, and the few concepts from the matrix calculus that we have already gone through in few of our last two video, right? Okay, so I am making this assumption that you are good at probability, and from there I will be starting this probability review. Okay, let's first of all talk about the Gaussian or the normal random variable, right? And we have already seen this Gaussian or the normal random variable. If I ask you what will be the probability density function of this Gaussian random variable, so let's suppose that this Gaussian random variable is this x, and it takes the value that is little x, and this takes the value from any real space, right? Then we have seen the probability density function of this random variable x, that is equal to 1 divided by root 2 pi sigma square exponential x minus mu ka whole square divided by 2 sigma square, and here we will have also minus sign, right? And what is this mu? So this mu is the mean of the distribution. And what is this sigma square? So this sigma square is a variance of the distribution, right? And this term 1 divided by root over 2 pi, so this term, so we are just making the adjustment so that the integral over this PDF from minus infinity to infinity, that means the total probability should add up to 1. So in order to make this adjustment, we need to have this constant, so that is why it is reflecting here, right? So before I proceed further, you should have a good understanding of what is mean what is variance, you should have the intuitive understanding of what actually the variance is or what the mean is. So let me just give you here the review. Let's suppose we have this random variable and that is normally distributed and it has the mean at 0, right? So and what does this variance tells you? The variance tells you about the spreadness of the distribution, right? If variance is high, then the distribution would be more spread out. And what does it mean by distribution having that is more spread out? That means the occurrence of the higher values of x will have some probability, right? Let's suppose if the distribution is like this, like it is more spread out, right? So we have some probability that the higher values of x could occur, right? Let's suppose the distribution is like this, right? So we have the 0 probabilities of these occurrence of these higher values, right? So the what does variance tells you? The variance tells you that how the distribution is distributed, it is more spread out or it is more narrower. If variance is less, then we will not have much wider distribution. It will be some around the most of the data would fall some around this mean, right? And occurring of or having the probability of these higher values of x will be very unlikely to happen, right? So you should have at least the understanding of what actually the variance and what is the mean, right? And we have already discussed all these things in a very detailed manner in our probability and statistics course, right? Now depending upon this mu and the this variance, you will get the that means these two parameter will determine the shape of this distribution or the shape of this normal or the Gaussian distribution, right? If variance is less, then the shape would be more narrower. If variance is high, the shape will be more spread out over the higher values of the x. And this mean will tell you that where to shift this distribution, right? If mean is 0, then the distribution would look like this. The mean will be at 0. If mean is, let's suppose 1, then the distribution will get shifted to the mean of this distribution will get shifted to 1, right? So this is giving you the shift, and this is telling that the variance is telling that if it is more spread out or if it is the shape of the distribution is more spread out or it is narrower, right? So we have already talked about this single random variable, Gaussian random variable. Now let's let's suppose that this x now takes the value that is from the n-dimensional space, right? So basically we are just talking about the multivariable setting, right? Here we have just one single random variable, and now what we are saying that, so basically we are talking about the multivariate Gaussian random variable. So now here this x will take the value from n-dimensional space. That means this random variable or this random vector will have the component that is x1, x2 and xn, and all these xi, that is x1, x2 and xn, are random variable, right? So we are just talking about the Gaussian random variable in multivariable setting, right? Now if I ask you how the distribution or the probability density function of this random variable will look like, so let me give you the direct expression of this multivariate Gaussian random variable, right? So let me first of all write that one. So now here the x is a vector, right, that will have the n component, and that is the PDF, that is the probability density function, is equals to 1 divided by root, or let me write like this, 2 pi to the power n divided by 2, determinant of this matrix. So here this sigma is a covariance matrix, and I will tell you what kind of information this covariance matrix will give you. The square root of the determinant of this covariance matrix, exponential half x minus mu. Here x is a vector, and this mu will also be a vector. And what kind of vector it will be, I will tell you. The transpose of it times the covariance matrix ka inverse times x minus mu, the transpose of this vector. So if you look at this probability density function of, in case of the multivariable setting, then it looks kind of same that you have seen in case of the single variable, right? Now here, since we are dealing with the vectors, so everything will be a vector or a matrix, right? Now let me give you the further infos, what is what here. So here the x belongs to some n-dimensional space, and this mu will also be a vector, and it will have also the n component, right? So this is the mean vector, right? So, and all these random variable that you see, x1, x2 and xn, all these will be marginal probability density function, right? And you know what is marginal probability density function, right? So if you look at the mean of this random variable x1, and this is nothing but just a marginal density function, the mean of this will be, let's suppose, mu1, and the mean of this will be mu2, and the mean of this marginal PDF would be mu n, and you just need to put all those mean as a component of the vector, and this will form you a vector, and that what we are calling it as a mean vector, right? And here the sigma, this is a matrix, and it will be a square matrix of size n cross n, right? And this is the covariance matrix. We will talk more about this covariance matrix, right? And here this is nothing but the just the determinant of the covariance matrix. Now if you look at this term, this, so here the transpose will be not there, so here, so if you look at this term, so it will look kind of similar to what you have already looked at in your linear algebra course, right? And while reviewing we have gone through this form. So this form kind of looks similar to the quadratic form, that is x transpose ax, right? So this is a vector and transpose of it, this is matrix, right? And it is a square symmetric matrix. So you will see that this covariance matrix will be a square symmetric matrix, and it will be also a full rank matrix. So the inverse of that covariance matrix will always exist, and this is again the same vector here, right? So X transpose AX. So this is kind of a or look like that is of a quadratic form, right? Now let's talk about a little bit about this covariance matrix, what kind of information that it captures. So this covariance matrix, so you have the random variable. Let's suppose you have two random variable. So we have this vector, random vector x, that has the two component x1 and x2, right? Now if I tell you that find the covariance between these two random variable, that is x1 and x2, right? So you will go and you will find the covariance between x1 and x2, or you might find that covariance of this random variable x1 with itself, or you might find that the covariance of this random variable x2 with x1 and covariance of this random variable x2 with itself, right? So this matrix, what you need to do, you just need to put all these covariance as a component of this matrix. So you are just going to form this matrix. And how we are going to form? So first of all, we are going to take the covariance. So let's suppose we are just talking about the case where we have two random variables. So this sigma will be 2 by 2 matrix, and it will have the 4 components. So you take the covariance of random variable x1 with itself, and then you take the covariance of random variable x1 with x2, take the covariance of random variable x2 with x1, and take the covariance of random variable x2 with x2, right? And we know what is the covariance of, let's suppose, random variable x with itself. It is nothing but the variance of this random variable x, right? So we can write this as the variance of this random variable x1, and here we will have the variance of this random variable x2, and here we will have the covariance with x1 with x2, and here we will have the covariance with x2 with x1, right? Now you can think of a general n by n covariance matrix. So at the diagonal position you will have the variance, and off diagonal that are not diagonal will be the covariance with random variable with some another random variable, right? And if you recognize here from this 2 by 2 matrix that these two quantity will be same, the covariance of this random variable x1 with x2 or the covariance with random variable x2 with x1 will be the same, right? So overall the point is here, the matrix, this covariance matrix or any n by n, any general covariance matrix will be symmetric matrix. It is square, so this covariance matrix will be a square symmetrics, and it will have the full rank, right? Now let me ask you, so what kind of information this covariance will contain, or what kind of information this covariance matrix will give you? It has the variance as a component, as a diagonal component, and it has the covariance as well, right? So variance will tell you that about the spreadness of the distribution. If variance is less, then the distribution would be more narrower, right? If the variance of x1 is less, then distribution would be more narrower, right? And what about the covariance? So covariance between two random variables tells you that how these two random variables are related to each other, right? And we have already gone through what is the covariance, what is the variance, right? So if it turns out that the covariance of random variable x1 with x2, that is greater than 0, what does it mean? That if you increase the x1, then x2 also tend to increase. That means they are in the sync, not exactly sync, but if x1 increases, then x2 also tend to increase, right? Then we say that the covariance is positive. Then x2 also tend to increase, right? And if you are not having the intuition of this covariance and the variance, I would request to go and watch these lectures of the variance and the covariance from my playlist. You will have the better understanding. And if the covariance between these two random variables, let's suppose, is less than 0, then if x1 increases, then on an average, or x2 tend to decrease, right? So if x1 is increasing, then x2 will go opposite to x1. Not exactly, but if x1 is somehow trying to increase, then x2 would go in or will increase in the opposite direction, right? Then in that case, we say that the covariance is less than 0. And if the covariance between these two random variables is 0, then we say that the x1 and x2 are uncorrelated. That means x1 and x2 are uncorrelated. They do not influence each other linearly, right? So the point here is that this covariance matrix basically captures both the spread of each random variable and the relationship between the variables, right? How they are related to each other. There is one more thing about this covariance matrix, is that this covariance matrix is always a positive semi-definite matrix for any kind of distribution. And I hope you must be aware that what is positive semi-definite. Now let's look at few of the examples. So let's assume that you have this random variable x and it has two components. So that means we are having two random variables, x1 and x2, right? And this is the covariance matrix and this is the mean vector. So what kind of information, or so basically these two are the parameters that are going to determine the shape of the distribution, right? So if you look at across the diagonal, so across the diagonal we get the information about the variance of the marginal probability densities function of this random variable x1 and x2, right? So the variance of this random variable x1 is 1 and variance of this random variable x2 is also 1, right? So if you look at x1 across the x1, then the spreadness across the x1 and spreadness across the x2 will have the same, right? And the mean is at 0, right? And if you look at off diagonal elements, that gives you the information about the covariance of this random variable x1 and x2. These are 0, right? So that means the random variable x1 and x2 are uncorrelated, right? So ultimately, by looking at this covariance matrix and this mean vector, you can comment that the distribution would be some kind of symmetrical distribution, and this is the contour plot of this distribution. And I think you must be aware that what is a contour plot, right? And many times I have discussed about this contour plot in my lecture. Now if you look at this example 2, the covariance matrix. Now so these the covariance element or the covariance between random variable x1 and x2 are 0, so that means they are uncorrelated. But if you see, in comparison to this covariance matrix, this variance of random variable x1 and variance of this random variable x2 is less than 1, right? So that means in comparison to this distribution would be more narrower, right? Because the variance in x direction and x2 direction, x1 direction, x2 direction is less than this, in comparison to less than this variance, right? So overall it will be more narrower, that means it will have the more height than this distribution, right? And again it will be symmetrical, and this is the contour plot, right? And if you look at this covariance matrix, and now if you compare with these covariance matrix, then you can comment about how the distribution would look like in comparison to these, right? It has the 1.5 variance in x1 in x2, and the random variables x1 x2 are uncorrelated, so it will be more spread out than these two distribution, right? And it will, if it is more spread out, that means the height of the distribution would be less than in comparison to these two, right? And if you look at this example, so in x direction, in x1 direction we have 0.6 variance, in x2 direction we have 1 variance. That means if you look at in x1, then it will be little bit narrower than this x2. So if you pick any marginal PDF across this by fixing this x1, if you look at any marginal PDF of x2, so it will have the more spread out than any marginal PDF of x1, right? So you will get this kind of distribution, right? Again and again the covariance, that means random variable x1 and x2 are uncorrelated, right? Similarly for this case, now coming to this case, we have the variance of 1, but now we have some covariance, right? And the covariance tells you that about these random variables x1 and x2, if we have some positive covariance, that means if there would be some relation between x1 and x2, that means if you increase the x1, so we have the positive covariance, right? That means if you increase the x1, so you can look at the plot of the contour plot. So this is the x1 direction and this is the x2 direction. So if you increase the x1, so if you are increasing the x1, right, then x2 also tend to increase, right? So that is what you mean by the positive covariance, right? And in this case the covariance is more than this case, that means x1 and x2 are strongly related than this case. Now if you look at this case, the covariance is negative, right? That means just look at this contour plot. So this is the x1 direction, this is the x2 direction. So if you decrease the x1, right, then x2 tends to increase, right? And in this case the random variable x1 and x2 will have the strong negative correlation, right? Because in comparison to this, we have more negative, we have found the covariance that is more negative than this, right? So alright, and if you have the vector, the mean vector other than this 0. So depending upon this coordinate, the mean of the distribution will get shifted to that position, right? So this is how the distribution would look like. Alright, I think you now should have a good idea about the multivariate Gaussian random variable, right? So in next lecture we will have a few components from the statistics, and there we will discuss about what's the role of the probability and the statistics in machine learning. So that we are going to discuss in the next video, right? And afterwards we will be jumping to the machine learning core subject. That is all in this video. Thank you so much.